Real-time characteristics of ROS 2.0. Evaluating the real-time performance of ROS 2.0 in system and communication layers. Aging and low fidelity. Robots emerging as alternative to human productivity, increasing service robots demand, and distributing robot system. Complex control software, synchronization of multiple controllers. Limitations of ROS 1.0. So we are talking about the older version of ROS. Real-time real-time constants. ROS does not 0.1 does not satisfy real-time requirements. Communication overhead, host guest system introduced delay affecting performance. Extensive modification, hybrid OS approach requirements modify ROS liberalities. ROS 2.0 improvements. DDS middleware enables real-time communication, scalability, and security. RTPS protocol, real-time publish, subscribe, multicast, and UDP. QoS provides benefits like real-time reliability and durability. Evaluating ROS 2.0 real-time performance system layer analyzes the dramatic behavior and schedulability of tasks. Communication layer measures message loss rate and latency between nodes. Compared to ROS1, comparison to ROS1, access suitability of ROS 2.0 for real-time applications. Software stack performance. Scheduling latency. ROS 2.0 exhibits lower latency and more domestic behavior. Task priorities. ROS 2.0 nodes meets deadlines better than ROS 1.0 in multitasking. Response time analysis. ROS 2.0 takes satisfy real time and constant unlike ROS 1. Communication performance. Message loss. ROS 2.0 maintains stable communication up to 1.104 bytes. Communication latency. ROS 2.0 exhibits lower latency than ROS 1 in all conditions. Multi-agent service robot. Front end. Web-based GUI for user interaction. Back end. ROS 2.2 system generating robot commands. Mobile robots. Kobuki 2 and Tetra DS4 service robots. Multi-agent robot performance. Productivity. ROS 2.0 exhibits dramatic behavior under stress. Traje- trajectory tracking. ROS 2.0 follows Brezer curve accurately, unlike ROS 1.0. Real-time word validation. Multi-agent robot system satisfies real-time constant. Now let's talk about software stack evolution. This section describes the performance of evolution of ROS software stacks that focus on real-time performance in the development environment for ROS-based systems. Real-time scheduling in the OS must be possible to meet real-time constraints. Additionally, in a multiple tasking environment where multiple nodes are running, each node must meet deadlines. Therefore, the experiment conducted the performance evaluation with two metrics: the real-time suitable of a Linux kernel that constitute, uh, conti- constitutes the software stacks and evolution of the nodes in a multitask environment. We confirmed that determini- the deterministic behavior of the software stack, which is an important indicator in determining the safety of the system, and we evaluated whether the node could safely of the system, and we evaluated where the node could be evacuated while satisfying the hard temporal deadlines. In addition, the stress ng tool was used to generate the CPU memory and I/O loads of the system. This stack was performed to assess whether the system was capable of stable operation even in unstable environments. Let's study about scheduling a latency. This section deals with the evolution of the scheduling latency between ROS 1 and ROS 2. The performance equation was performed using the benchmark tool called cyclists. The implementation software stack architecture is shown in Figure 1 because ROS 1.0 does not officially support any RTOs. It was implemented on top of the standard Linux. On the other hand, ROS 2.0 was developed to meet real-time constraints when implemented on RTOS. In this article, we have uti- utilized the Linux kernel patched with the primit. Shows the result of evaluating the scheduling latency in the ideal environment. The scheduling latency is defined as the time differences between actual task anti-evaluation time and configured period. In our evaluation, we configured as a single real-time task to run with a period and deadlines of 1 ms. To ensure that the multi-core hardware did not affect the result, we configured the computer's CPU efficiently in of to task run on CPU 0. These are the diagrams which shows the CPU latency with us. About message loss. Message loss evolution was performed on a one-way communication method. If a message sent from a PC was received at RTI3 to verify the limits that the system could send and receive messages stably without losing messages. A performance evolution was performed according to the communication frequency and data. Table 8 shows the result of message loss evolution of ROS 1.0 and ROS 2.0 in both the ROS 1.0 and 2.0 systems. There was no message loss regardless of communication frequency until the data size of message was 104 bytes. However, the result tested at 105 bytes data size indicates there were message losses at frequency of more than 100 Hz, which makes it impossible for suitable operations in both the systems. However, when implementing a ROS-based system, a situation can arise in which a node communicating at frequency of 100 Hz or more must be implemented. Therefore, for their systems to be able to communicate stably without losing a message, the size of the message should not exceed 10.4 bytes. In this next section, the communication frequency evaluation be performed by 10 to the power 4 bytes, which is data size enables stable communication. Conclusion: real-time performance 2.0 outperforms ROS 1.0 in satisfying real-time constants. Multi-agent robots ROS 2.0 enables suitable and dramatic multi-agent system future development promising for engineers to build real-time robotic system. Thank you for watching my video. Please do like, subscribe, and share this video as soon as possible. I am Shishi from Sri Venkateswara College of Engineering, pursuing studies of second year from second year engineering CSE branch. Thank you so much. Bye bye.